Okay, so let's resume now. So Kyle also not just physics.
Hi everyone, my name is Kyle. I think I would like to first begin by thanking the organizers for giving this opportunity to talk about my work. I'll talk about jet physics at the EIC and medium modifications. This question I'll mainly focus on EP and PP as a baseline, but I will also discuss some observables that are interesting to see to test medium modification as well. Of course, at LHC, jets are produced copiously. In fact, 60 to 70% of the ATLAS and CMS analysis has jets in their analysis. So it's hard to overemphasize the importance of studying jets at the LHC. But EIC is a completely different environment and thus provides different opportunities and also different challenges. With smaller center of mass energy compared to LHC, the PT of the jet, typical jet produced at the EIC is much smaller than the PT of the LHC, jet at the LHC. I don't know why I put square root there. And also the multiplicity of the jets are much smaller in EIC compared to LHC. Also because it's more cleaner environment with smaller center of mass energy and also electron beam, you have less contaminations coming from underlying events and pileups. So with the success story of LHC, we want to use the jet studies at LHC as a guideline to studying the jets at the EIC. And I'll try to draw some comparisons throughout the talk, how the EIC case compares with the LHC case, and point out some of the important challenges and opportunities that are crucial in studying the jets at the EIC. And one of the first questions that I want to pose is, what is the role of higher power corrections at the EIC? Since depending on the processes you're looking at the EIC, the only hard scale, sometimes in the EP collisions, the only hard scale that you might have is the PT of the jet. So if the PT of the typical jet is as small as 4 to 5 GeV at the EIC, the higher power corrections can become important, and factorization braking effects can happen. So I'll discuss a little bit of higher power corrections of these kinds. Of course, jet is an interesting object to study on its own, but it has many other interesting applications. One of them being it is a precision probe of QCD. It can, for instance, depending on subprocesses you look at, you can constrain different non-perturbative PDFs using jet studies, or you can do a precision determination of alpha S. I'm not going to talk about it in this talk, but one of the interesting applications that a lot of people have been talking about is using soft drop jet to, for instance, determine these strong coupling using the jet study as well. So what is the role of jet as a perturbative probe in the EIC? Can you actually use jet as a perturbative probe just like it has been used at LHC to study these non-perturbative objects first, for instance? And of course, jets can also constrain different BSF models or give you a probe to study Quark Gluon plasma. So maybe you can also understand different classification of different type of jets at the EIC, just like how you classify BSM jets or Quark jet or Gluon jet in LHC. Or you can study core nuclear modification in the EIC compared to LHC case. And again, LHC event is a lot more violent compared to EIC case. This is a typical event in LHC and HERA, and you can see there are a lot less lines going through in the HERA events. So with much cleaner environments, what is the role of non-perturbative physics at EIC? Since there is a reduced self-contamination coming from underlying events and pileups, can you actually expect reduction of those non-perturbative physics playing a role in EIC? So these are, throughout the slides, I'll actually point out each of these red points that I wrote down in the introduction. So plan of this talk is first I'm going to talk about inclusive jets, that is jet measured without any substructure. Then I'll extend the formalism to talk about jet substructure measurements. Sorry, I didn't mean to put at the LHC, just jet substructure measurements. And then I'll talk about subtractive moments, which is another interesting observable that I want to propose as a way to study media modifications. So inclusive jets can be studied as, of course, different processes. You can have lepton unobserved, final lepton unobserved, in which case you don't have a Q-square measured. So the only hard scale is the PT. So you require high PT scale in order to have a factorization. Or you can have a deep inelastic scattering where you have a lepton observed to constrain the Q-square, but you require both Q-square and PT to be high. Or you could even study photoproduction where the photon you have is nearly on shell by requiring the Q-square to be small. But you still need to have a high scale, so you require the PT to be high. So in this talk, we're going to focus on the photoproduction, but you can look at these papers to look at the other processes, studies on other processes. So at next leading order, these are some relevant subprocesses, so you have to look at it in EP collisions. There's, of course, leading order DIS, where the photon can behave hadronically and give this kind of result processes. Or photon can directly interact with the Quark or the gluons and give you this type. But at photoproduction, leading order DIS does not contribute to high PT production of the jet. If you require the photon to the Quark to be have high PT, then the Q-square becomes high. So you cannot have a leading order DIS contributing to photoproduction in the high PT case. So you only have these kind of 2-to-2 diagrams that contribute in the photoproduction case. And such photoproduction, of course, can be studied not just for these processes can be studied not just for jet but you can do inclusive hadron studies, right? You can just replace these jet with hadrons, and you can have inclusive hadron studied at high PT or high PT and high Q-square or photoproduction as well. And such study has been done in 2003 for photoproduction using hadron instead of jet. And you can factorize such contribution of the direct or result. Sorry, this cursor is bothering me. Direct or result into a non-perturbative PDFs and also the fragmentation function that describes this hadron fragmentation. And of course, there's the hard vertex, which can be perturbatively computable. And then again, you observe the final lepton to tag Q-square and require it to be small so that you have a nearly on-shell photon. And you can do the same thing where, similar thing, this is an unpolarized cross-section factorization, but you can also factorize it for the polarized case as well. And it was found that even at square root of 100 GeV, which is a smaller than the maximum expected projected center of mass energy for EIC, measuring asymmetry gives you a sensitivity to these polarized PDFs. So you can do a two-extreme thing where the polarized PDF is identical to the unpolarized PDF case, or is identically zero everywhere. And the two different scenarios are discriminated by measuring these asymmetry. And actually at low rapidity region, it gives sensitivity to the polarized Gluon PDF. And at high rapidity region, it gives sensitivity to polarized photon PDF. But remember, this was a study done using a hadron, final hadron observed. So there was one crucial assumption that was made, which is that the fragmentation function is well determined. So there is no uncertainty coming from fragmentation function of the pinon, which was used in this study. But you don't have to make this assumption if you use inclusive jets instead of the fragmentation function, because inclusive jet is a perturbative probe. It's perturbatively computable. So you can repeat this kind of study where you replace the fragmentation function with jet. In fact, there was some study done using PDF fits of HERA with and without jets, and you can see when you do with jets, study with jets, the fit with jets actually has a much reduced uncertainties for the Gluon PDFs. So again, here is the red part. The jet plays a role as a perturbative probe for EIC. So how can we factorize these cross-sections with jet observed instead of hadron observed? You simply replace actually this, it turns out you just simply replace this fragmentation functions that describes the hadron fragmentation with what we call semi-inclusive jet functions. So now this perturbatively computable jet function plays the role of this non-perturbative fragmentation functions. So there is one less non-perturbative functions, universal functions that you need to fit with. However, there are, when you look at this factorization of this jet cross-section, there are these power corrections that enter. One is of order R squared power corrections, which turns out to be very small. But another power corrections that are only relevant. Sorry. Right, sorry. So R is a parameter that describes the jet radius.
So when you say that they turn out to be very small, you mean even for large R, or?
Yes. So even for the large R, this factorization actually agrees very well with the fixed order calculation, which actually accounts for these kind of power corrections. And it turns out this is true whether you have substructure measures or not. For all the substructure that we have measured so far, these R squared power corrections seems rather small. Yes?
It's the question, so that jet function depends on R, presumably.
Yes. Sorry, I didn't write any functional dependence there. But you can write an operator definition of these jet functions and everything. But here, there's this other source of power corrections that no one really talks about at LEC because the PT of the jet is typically much higher than lambda QCD. So this power correction is not of concern at LEC. But at EIC with PT going as low as 4 GeV, you can really have some power correction effects that can mess up this factorization. So yes, it gives sensitivity to photon PDFs, both for polarized and unpolarized case, and there are still role of power corrections that you need to investigate. So we did some preliminary study of unpolarized inclusive jets for photoproduction, and so this is a comparison with the PTF at PT of the jet greater than 10 GeV and R is equal to 0.8, and it shows actually pretty good agreements. But again, notice this form of the power correction is lambda QCD over PTR. That is because you're observing a jet, there is actually another scale that's produced from this factorization, not just the HAR scale PT, but also this, what we call jet scale PTR. So since PTR is the smaller scale of the two, the power correction really can be important when the R is very small. So you have to really compare the lambda QCD with this PTR. So we're in the process of studying some power corrections of this type. And it seems like when you reduce the PT to be, for instance, 5 GeV or reduce the R to be something smaller than 0.8, the mismatch between the PTI and the theory calculation seems bigger. But still, even at 5 GeV, it seems like agrees relatively okay. But there seems to be some power correction effects.
Is this EP or EA?
This is EP.
When you think about EA, you also have E to the 1/3 enhancement for your power correction. So it gives
Right.
just the standard saturation for but probably applies here.
Right. Yeah.
We won't be able to actually measure that. It would be cool to actually measure that.
Measure that. Yeah. Okay. Sure.
Then it would be not lambda cube, you could guess, you know what I'm saying?
Well, lambda QCD times square times E to the 1/3 is, PS proportional to PS squared.
There will be also energy dependent because
Could be also 1 over X, the same power.
X is low.
So
So
This is not very
yes, it
that's why
will be like jet quenching effect. It will be really jet quenching effect in PA.
large X, but large.
Big momentum broadly and all that.
Well, I thought that's the topic of the talk, right? Medium effects.
What's that? Yeah. I'm also going to talk about. I'm actually not going to develop the formalism on EA, but I'll also talk about some medium effects actually in this slide a little bit.
Let me ask on the PTR side, how they include the power correction?
These lambda QC over PTR power corrections, I don't think you can actually really do anything about that because you want always the hard scales to be something higher than the non-perturbative scale. Whereas there are these power corrections that can be accounted for by doing legislative power factorization. Whereas these are really compared to the non-perturbative scale itself. So I don't think.
Yeah, hadronization, you have a cutoff.
Yeah, no, that's for sure. That's in the vacuum, but in the medium, we should have a medium effect, right? It's much harder than that because you press on next with press. It would be interesting. That's the point. Having a nucleus.
I didn't think Lydia had anything to say about
Well,
that.
definitely, but I was what you compare to PQC with PTR, of course they coincide because they're both PQCT.
No, but none of on that comparison, nothing contains power corrections yet, right?
So then comparison is always working, right? Because you compare two theoretical operations based on the same phenomenon.
I think Larry was asking the same question a few weeks ago, and I think the conclusion was that PC is not quite perturbative.
Of course, sure, they have a validation, they have a lot of other.
So, do you have hadronization in PTR?
Yes.
All right. So here basically what you're saying is that hadronization doesn't matter much.
That, exactly. So in that sense, you're right. The effect of lambda QC coming from hadronization is not important. That's
Right.
For chat.
Well, still, I mean, even for jet,
You could.
precision.
And then there was also a question of whether the calculation that compared this NLO and NLL and PCI, I think it's only
depends what to, yeah.
No, it contains next to the.
Yeah, this is next to me.
next to
The evolution is NLL.
Well,
But
the
not
way you look at
NLO.
legal,
Not NLL, right?
but not NLO, right? And the view, the net calculation.
This is NLL.
NLO plus
For the hard process, right? What NLL for the hard process?
I believe so. I mean,
it doesn't have the full NLO, but probably it's marginal.
Right, so there is no fixed order matching, but this also can be done. But it turns out so the only reason why you would want to do fixed order calculation next with linear order is to capture this R-squared effects. But even at R going to 1, this turns out to actually give same prediction as the fixed order. So
Because I just collinear probably. So that's why it doesn't really matter very much. So that can like check out.
So this is the inclusive jet studies, but you can also try to probe inside the jet and try to observe different substructure, of course. And one of the most interesting, I think, observable to this community is jet angularity. Jet angularity is a generalized class of IR safe observables that has this parameter A that with different A, of course, you can have sensitivity to collinear radiations of different amount. So for instance, if this A is equal to, as this 2 minus A exponent gets smaller, you have a stronger sensitivity to the collinear radiations, right? Because this is an angle with respect to the jet axis of the partons inside the jet. So if this 2 minus A, for instance, becomes 0, where A equals 2, this factorization actually fails because you are infinitely sensitive to the collinear radiations. But you can actually show that factorization works up to A equals 2 or below 2, and then you can tune this A values at different amount. And I think this is interesting observable because this actually has 2 special cases that many experimentalists like to measure. And A equals 1 is actually corresponds to the Girth or the jet broadening case. And A equals 0 corresponds to the jet mass or jet thrust case. And you can actually see in the ATLAS and ATLAS event experiment result, you actually see RAA enhanced for Ger's case, whereas it's relatively flat for the jet mass case. So it'll be interesting to study this kind of angularity observable with tunable parameter A to see how these medium modifications changes as a function of it.
The jet PTs in those two are very different.
That's this is 40 to 60, and this is 120 to 150. But here in this ATLAS studies, I think it goes up to much higher.
Yeah, but the 40 GeV jets start to fragment still in the lead medium.
I don't know if this. Do you know if this paper is 40 to 60 the high spin that they're looking at? I don't remember.
I have to check.
Yeah.
Alice runs out of statistics.
Yeah. I mean, either way, I think it'll be interesting to maybe look at both of them at the same kinematics and see how the RAA changes.
Do you know why there's no PP reference compared to?
PP reference of.
I can answer that question, and that is that the PP reference run is part of the heavy ion run at the LHC, and Alice is slow, and so it's hard to collect enough statistics. The long LHC runs, which are great for collecting statistics, are at much higher U.S. There has been a run taken and a 5 GeV comparison for that too. So hopefully that'll be a decent jet measurement. I think there will be.
So this jet angularity has this label tau, and probably that reminds you of the thrust variable, thrust tau in the event shape. And that's where this angularity really comes from, studying these event shapes at the hemisphere in the E plus E minus. And that's how generalized thrust or angularity was defined in E plus E minus in this sense. But when you apply to PP, because you want to have a boost invariant parameters, you actually have to change this energy into the PT of the jet. And that actually corresponds to E plus E minus definition up to power corrections. And these power corrections are, again, are not of an issue because the tau at typical value of the angularity at PP is actually much smaller. It's very small. But at the EIC, with these tau being larger, these power corrections can be of issue as well. So these are another source of power corrections that can be done. And at A equals 0, this actually corresponds to mj squared over pt squared. And so you can see already here, if pt is really high, then compared to the jet mass, which is the case for LHC, such power corrections are rather small. So how do you factorize your framework to study jet angularity? It turns out to see that this is the jet function that I showed for inclusive jet case before, which has R independence, as someone asked. It turns out to you simply replace such semi-inclusive jet functions with now what we call angularity measured semi-inclusive jet function. And at this region where tau is much smaller than R squared, this can be actually refactorized into different modes that describes physics at different scales. And again, these refactorization actually requires power corrections of the same tau. So the point is, in this factorization work, you have to actually really use these two definitions of angularity interchangeably in order to derive this factorization. So whatever of these size power corrections are can actually make this factorization fail. And these modes describe physics at different scales, meaning they come with some sort of typical scales that they want to be in. And this is the green, for instance, describes the hard collinear mode, and red describes the collinear mode, and blue describes the soft modes. And I won't get into the detail, but these modes come with their own RG equations, and evolving these RG to common scale gives you a resummation, joint resummation of logs of this type. But one thing I want to point out is that one of the mode that we call collinear soft mode is the softest out of all these different typical scales that they come with. And they are, the soft mode is proportional to this angularity variable tau. So if this angularity tau becomes very, very small, then this scales become non-perturbative. So this angularities or jet substructure observable, or jet substructure observable is also sensitive to non-perturbative physics when the angularity variable becomes very small. So I want to discuss briefly about different non-perturbative effects that are important in PP collisions and possibly EP. And first, one of them is multi-parton interactions, or MPI, or underlying events, which is multiple secondary scattering of partons within the protons that may produce soft particles and contaminate the jet. Or pileups that come from secondary proton collisions in a bunch that may also enter and contaminate the jets. And of course, there's always hadronizations because the partons forming the jets will eventually hadronize. And these non-perturbative radiations will change the distribution because it talks with the soft scale, as I said. And it turns out you can write this distribution effect. You can actually combine it turns out you can take your perturbative distribution of the factorization that I developed before in the previous slide and convolve it with what we call non-perturbative shape functions, what's called non-perturbative shape functions, to describe the full distribution. And it was shown, and it didn't have to be that way, but this non-perturbative shape function turns out to be very simple. It was shown in this paper that it is sufficient to consider a single parameter non-perturbative shape functions to describe these MPI and hadronization effects. And this parameter omega actually can be related to the typical momentum component size of these soft radiations. Therefore, if this omega is of the order hadronization scale, then this would imply that the non-perturbative effects that you have in your experimental result is only corresponds to non-perturbative effects coming primarily from hadronization alone. But if there are other sources of non-perturbative effects like MPIs or pileups, you can have this omega much larger. But one way to think of it is your momentum, individually these MPIs or pileup can be very small, but they can add up and produce a large components. So this is PP results. So as you can see, the perturbative results do not agree very well with the data, LS data. But once you convolve with this non-perturbative shape functions, then you can actually describe the data quite well. And here, the omega parameter that you had to use was 8 GeV, which is much larger than hadronization scale, which means that there are actually a lot of MPI and pileups.
How do you get lots and lots of MPIs in PP?
How?
Yeah. If you told me AA, I'd believe you, but PP seems hard to get lots of multi-parton interactions.
I mean, one way to test it is, I'll also describe how this can be accounted for PP in next few slides. How I can be sure that this is really an MPI effect. Maybe that will answer your question.
Yeah.
Okay. So one way to get handle of these MPI effects, which are difficult to understand, is do what we call what's called soft drop grooming. So you can these uncorrelated radiation pileups or MPIs are generally wide angle soft radiations. So you can actually do some iterative procedure called grooming. I won't describe it in detail, to get rid of sensitivity to these wide angle soft radiations. And that's what we did to extend our formalism. And in order to describe the data now, the omega parameter that you needed is actually 1 GeV of the order of hadronization scale. So really, compared to this case where there is no grooming done, it was 8 GeV. But once you do grooming, the PP data can be described as 1 GeV.
That doesn't mean that the most of the effect that the non-perturbative effect that you put in this shape function was not coming from multi-particle interactions, but was coming from large angle of wide angles of radiation.
Right. So actually, you can also go back to this paper. They actually tried to turn on and off these MPI effects to see how much of these shifts are corresponding to MPIs in PDF. And they have actually shown explicitly that when you actually turn on these MPIs, these omega parameters has to be larger than 1. And we have done some testing on that way as well. But what about EIC? In EIC, you would typically have much cleaner environments. And as expected, here, this is it's just a perturbative result compared with the PITIA. And without any convolution with these shape functions, without any shift, you can see that generally they agree quite well. So think of this as analogous case to this, which has a large shift, whereas here you don't really see a big shift.
That's surprising because you said that you expect to have actually two power corrections, right, which can be translated into somehow. Right. So I want to distinguish the two. One is the power corrections of the type coming from the difference in the definition of the angularities of these types. And the other is the non-perturbative effects being the MPIs and pileups, which EIC has less sensitivity to MPIs and pileups. But the power corrections, of course, of these types, which are, for instance, mass square over PT square, can be sizable. And I haven't talked about that yet. I'll talk about that mention briefly about that too. But it turns out that the non-perturbative effects coming from MPIs and pileups seem very small. And indeed, this is just looking at, these are different R's. So they are both perturbative results. There's no convolution with the shape functions. But here, this is A equals 0, A equals different values. And if you look at A equals 0, R equals 0.8 results, that corresponds to this yellow and the PITIA results. So you can see, even though it's a small shift, there is still a little bit of shift compared to the PITIA results. Now, if you want to convolve the shape function to describe the hadronization effects, the typical parameter value that you need for this omega in order to describe this hadronization is of order 500 MeV, which is of order lambda QCD. So it fits with the expectation that non-perturbative effects in EIC mostly come from hadronization alone and not much of MPIs or pileups or anything like that. But as Yassin mentioned, there is also an issue of these power corrections, which can be important. And this is a plot that we produce where we got a distribution of these angularity distributions using the PP definition of the angularity or E plus E minus definition of the angularity and took a ratio. And of course, if the power corrections are small, we expect them to be precisely at 1. And depending on different A values you look at, you can see that the power corrections can be larger. This is logarithmic scale, so still most of the particles seem to lie at 1. But you can see this is PT, I don't know if you can see the label, but this is the PT higher than 10 GeV. This is PT greater than 5 GeV. You can see that PT greater than 5 GeV, as expected, has a higher power corrections. And again, this is also PT greater than 10 GeV. So when you look at PTA greater than 5 GeV, you might actually expect these power corrections to be larger. And you can also see here, like for instance, this one, the blue curves, where A is equals to -2, R equals 0.8, PT greater than 5 GeV. The peak is not really exactly at 1. So you can expect the shift coming from these power corrections as well. And smaller the R, you actually see that the power corrections are reduced. This might be counterintuitive because previously I said when I talk about inclusive jets, the power corrections will be larger when R is smaller because it's the smallest scale is PTR. But here, with the angularity measure, the smallest scale is actually of the order 1 over R. So smaller the R, the smallest scale actually become larger. So it fits with the expectation that smaller R has actually smaller power corrections compared to larger R case. Now I want to change the gear and talk about another interesting observable that I want to propose, which is called subtracted moments. Of course, heavy ion collisions produce a large number of uncorrelated soft particles contaminating the jet, as this shows, compared to PP and I think this is AA. And you can try to alleviate the problem by either developing a background subtraction techniques to identify true composition of the jets. You want to ideally do this jet by jet, but I don't think you can always do that. Or you can define an observable that is insensitive to such uncorrelated backgrounds. And one way to do it is use grooming, as I talked about briefly before in previous slides, which is a recursive algorithms that remove these soft radiations in the jet. Or you can define the subtracted moments, which is what I'm going to talk about. So subtracted moment is an observable that studies the correlation between the PT and a linearly additive substructure V. By linear additivity, I mean you can separate the contribution coming from the signal jet that is correlated with the PT and the soft uncorrelated emissions. To illustrate, an example is jet mass, or tau zero. I'll just call it jet mass because it's proportional to jet mass. Now, if you look at jet mass case, you have mass of the jet over PT square, which can be written as P minus and P plus over PT square. And if you take the P minus to be the large component of the jet, then the large component of the jet receives, of course, contribution both from the signal jet or the soft uncorrelated emissions like MPIs or pileups or other stuff. But they are approximately just signal jet because these are by definition soft. So the PT of the jet is more or less unmodified by these soft uncorrelated emissions. So you can actually, due to that, write this jet mass as a additive contribution coming from the signal and the contribution coming from the soft uncorrelated radiations.
Sorry, what's P plus versus P minus?
So this is just the Lycon definition of the.
So it's two components of your jet function.
Right. So the invariant mass is P plus.
And somewhere, if I dig through your slides, I'll find the equation for your jet function.
Equation for the jet functions? Not. What do you mean equation for the jet function?
Well, what is the jet function? What's the form?
Oh, well, I didn't write it here, but you can find it in. I can give you the references. So you can write this jet mass into a contribution coming from the signal jet. So only the signal is correlated with the PT of the jet. That's what we mean by correlated effects, and the soft uncorrelated emissions. And this separation and the fact that they are uncorrelated emissions amounts to actually what I wrote before, but now writing in terms of these plus and minus components. It amounts to your distribution taking this form, where there is some sort of function that describes these contribution coming from the soft uncorrelated emissions and a function that describes the contribution of jet mass coming from these signals. And because of this form, you can, when you take the moments, you can actually separate the moment into a contribution coming from the signal, the correlated emissions with PT, and the moment contribution coming from the uncorrelated emissions. So now if you take the difference of these two, and of course, experiments are often done with several bins of PT, and you can do a binned definition of this. And when you take the difference of the two, then you can see that this uncorrelated emission contributions to your moments cancel out between the bins. So what you're left with is, so when you define the subtracted moments, what you're left with when you take the difference is you can take such difference of the left side, or you can take the difference using just the signal side, and they give the same result because this part cancels out. So you can calculate this using the theory calculation of the perturbative calculation without doing any convolution. And you can calculate this side, for instance, using the experiment, and then see how well they agree. And we indeed see that the ATLAS data for 5 TeV or 7 TeV gives a good agreement. And we also ran a PTI simulation with and without MPI. And they all give same curves for this observable subtracted moments. So again, this is independent of the shape function x, so there is no convolution done at all. You can actually compare with your perturbative calculation of the theoretical calculation. And it's a useful tool, observable to test modification by medium with reduced sensitivity to uncorrelated radiations. But you might wonder, how far can we take this? We want to test the limit of these independence of uncorrelated radiations. So what we did was we took the PITIA without MPI, and then we added MPI, which also gives the shift. So again, this kind of answers your question before. You wonder how can you have so much contribution for MPI for PP, but you can see that there is actually a large shift from MPI. But or you can also add on top of that pileups events, like 7.5 average pileup events, or even 50 pileup events, and all of them just shrinks down to the same subtracting moments. So this observable is indeed insensitive to all these MPI or pileup soft radiations, which are uncorrelated. So this can be useful, observable to study at heavy ion collisions with reduced sensitivity to these backgrounds. But if you take this pileup events to a higher number of pileup events, we didn't test exactly where it fails, but if your pileup events becomes 200, 300, then the additivity that I mentioned earlier starts failing because the PT of the jet starts getting modified even by the soft radiations because there's so much of it. So this equation starts failing. So you cannot really do this to like probably 200 pileup events. So one way to remedy this was we defined another observable tau head where you no longer have this PT square in the denominator, but PT. And now this PJ minus, which is of the order 2 PT, cancels with this PT precisely, and the additivity is restored. And then we tested this subtracted moments corresponding to this tau head up to 200 pileup events, and you can actually see that this subtracted moment shrink down to 200 pileup event case gives you the same subtracted moment as the case without any MPI.
So it wipes out the MPIs as well as the pileup events.
Yes, it removes MPI as well as the pileup events.
Whatever those MPIs really are.
Yeah, I mean, there is a tune that in the PTI that says MPIs. So this would be a useful observable for studying jets at heavy ion collisions or high luminosity LHC. But of course, this observable should have some sort of discriminating power at heavy ion collisions to be useful. So one thing that we tested was we naively changed the fraction of quark gluon in our observable. So we said, so if this red is the typical gluon fractions as a function of PT in PP case, we can change the gluon to be suppressed further compared to the PP case, or enhanced compared to the total quark or gluon fractions, and try to see if those different fraction compared to PP gives you different curves to give a discriminating power. And indeed, when you take these two different models and calculate the corresponding subtracted moments, you can see that model 1 with enhanced quark gives you a curve right here, or model 2 gives you a curve right here, and they are actually separated from the red curve. So subtracted moment can actually have discriminating power on models that predict changes in quark and gluon fraction due to interaction with the medium. So whatever medium model you one comes up with, you can calculate the corresponding subtracted moments and see if they agree with the data. So the conclusion slide. I have developed a formalism for studying semi-inclusive jet production with and without substructure measurements. Then discuss the phenomenology of angularities, which are useful substructure to observe observables to test medium modifications. And going from PP to EP, we demonstrated that contamination from non-perturbative soft radiation was reduced. Maybe you can expect similar reduction going from PA to EA. Going from PP to EP, size of power corrections for inclusive and substructure observables for the EIC were discussed. And maybe you can also expect similar power correction effects going from PA to EA. Then lastly, I discussed subtracted moments, which were shown to be independent of soft uncorrelated emissions and can be useful to study jets in the high luminosity LHC and heavy ion collisions. Thank you.
Questions? Well, I have a long assuming this subtracting moments. Yeah, so this omega shift is assumed to be constant, right? I mean, event manner, right?
Right.
You expect, sensitivity to fluctuations from the event.
So you're asking how can you expect this omega to be constant in PP? So right. So this omega really corresponds to, if you look at this functional form, integration of k with this shape function f, and that actually comes from, in this derivation, you can see that it's actually coming from the plus components of it, which is not the PT. So PT dependence can actually be factored out completely, because you can going from the derivation coming from this how this jet mass contribution comes about from this soft uncorrelated emissions. This omega actually really has to do with the plus component. Yes.
So I actually had a question back to the nice story you told us about the power corrections and how using the smaller R jets gives you less effect of the soft stuff at the large angles. And you showed that the FBI and underlying effects are all smaller at EIC. And I found myself wondering, okay, so if we measure those things, what will we learn?
I mean, I guess that's more of a philosophical question.
No, not at all. Actually, it's an important question because when we design the detector, we have to optimize, right? So some things you can do really well. All the first versions of detectors do everything really well, and then reality sets in. And so then you have to kind of think, well, what are we going to learn the most from?
I mean, we can say that what you just said is exactly what we learned, right? That we're learning the limit of factorizations or power corrections, or limit of or classification of different jets, or role of non-perturbative effects in the EIC.
So should I look at this as a way to study hadronization?
I think that's also a fair point, because at the EIC you have, at least for EP collisions, the only non-perturbative effects that you have is really the hadronization with the reduction of these MPIs and pileups. So you can really say that you have a better handle of the hadronization effects.
Because everybody talks about measuring stuff having to do with hadronization, and more or less nobody knows what to actually go and measure. So, so then I guess what you're telling me is that I have to design my detector to be able to measure pretty soft jets, 5, 10 GeV, and then look at them with a smaller R and a larger R, and try to map out these hadronization effects. Is that right?
Right.
The power corrections on the nucleus have their own interest.
Exactly, that was my question. What's the difference between having a nuclear target and a photon target, from everything you said here? But after that, what we learned, EIC, where for nuclear target, that's some difference.
Well, it's one.
Well, I'm pretty sure you guys would tell us that if we only measured 1A, that we would not be doing our job. Right? So maybe you can map those nuclear effects by looking to see how those change.
Right. But if their goal is to eliminate,
well, but
you cannot eliminate it. Don't think you can eliminate this effect.
No, they're simply not included in the analysis. There's no nuclear effect so far, but it's like EP.
Right. You're saying they're
so everything interesting is behind that.
Which makes it cleaner somehow. Really, somehow, for HERA, probably be able to study that.
Well, you don't want to make your observables so clean that all the interesting stuff is gone.
You don't single out some effects, right? If you have
absolutely
computing effects.
Right. Yeah. So the plot that you had just a moment ago with the two energies of jets. Yeah, that one. So what that really said to me is that by changing the jet PT from 5 to 10 and the R from 0.4 to 0.8, you actually scan these effects.
Right, you can actually scan these effects. Sure. And actually, I didn't share it with you, but I've done some analysis on PT greater than 5 GeV case as well, and you can actually see that agreement is not bad. But seems like what you there is definitely a higher power correction effects, because you seem to find that this PTR results and the perturbative result seem to be closer than what you would expect. And it might be because this power correction is actually shifting the distribution to the direction that you want to shift anyways, which by including the hadronization effects. So one way for us to do that, test this is, and which we haven't done that yet, but this PTR result actually uses the one angularity definition that was used for PP, but you can also use the angularity definition of the EE and see how this PTR distribution actually changes from one definition of the angularity from the other. And if they are changing drastically, and of course it shouldn't change drastically, this is precisely that, but this is plotted in ratio, but you want to see in the distribution range how big of that it is. I mean, if I plot that, if the extreme case is that the other angularity definition gives you a peak here that agrees with this perturbative result, then you really cannot learn a whole lot about hadronization effects because you don't really know if the shift is due to hadronization effects or the power corrections. But if the shift is very tiny compared to this PTR results, then you can see that there is still remaining shift that needs to be done in order to agree with the
Like a technical, is it this PTR 6 or PTR 8? PTR 8 doesn't have a GIS mode in the time node, right? This must be the old PTR 6. And from what I heard, they're basically redoing everything from scratch because they said just the PTR 6 GIS is a pile of, okay, you fill in the next word. But
Yeah.
so they're redoing everything from scratch. So maybe all of this, I mean,
Yeah, this
they
is
probably want to repeat this whole analysis whenever the 8 with GIS is out.
yeah, this is yes.
To my knowledge, there's no PTR 8 GIS mode. Right?
Okay, there's no further questions. It's time.
Yes, so there's no discussion planned for the afternoon. So everyone is kind of